Have you ever thought about how complicated the process of watching these videos really is? I'm sitting here in the past compared to you, and the light from my face goes into a camera, gets converted into an electrical signal, goes thousands of miles away to a server, and then months later you download that to your computer and watch this? It's crazy. Electronics are awesome. Have you ever thought, why do we call them electronics? Well, it's because they use electrons. These electrons, which course through wires, have a special name in physics. We call them currents, which actually kind of makes sense for once. Finally, a science name that makes sense. Anyway, these currents of electrons travel between me and you. Let's put all of these electrons to work and study current.
Let's begin by reviewing our lesson objectives. First, we'll introduce current. Then we'll compare the flow of current and electrons, which strangely turns out to be a little different. And lastly, we'll compare direct current and alternating current. Let's go to our good old picture of our battery on a circuit. The battery here, represented in blue, green, and orange, has a negative terminal and a positive terminal. The blue line completing that square is the circuit, and our electrons are flowing through it. Notice they flow out of the negative terminal. Because they're negatively charged, they're going to rush away from that negative side, go through the wire, through the light bulb, do some work before racing back to the positive side of the terminal. And if I want to measure how many electrons are going through that circuit, I'm going to use current. Current is a measurement of the flow of electrons, specifically per second. So it's how many electrons go by per second. We could compare current to water running through pipes. You can really think about the fact that your electrons are sort of like water cruising through a metal. And if there's not much water going through, / not much electrons going through, we call that low current. On the other hand, if we have tons of water flowing through our pipes or tons of electrons flowing through our wires, we call that high current. Now, when we measure the flow of water, we might use something like gallons per minute. What do we use for electricity? Well, all of the circuits on this wall can measure their current in amperes. Another way to think about that is coulombs per second. And remember that coulombs is a measurement of charge. So we're basically thinking loosely here about the number of electrons that are cruising by every single second. Let's take a typical device you might use. I don't know if you've used one of these. They're called phones, and you use them to make calls. But actually now we don't do that so much. I digress. The point is, what is the current through your phone? It turns out it's 1 ampere. Now, what does that mean? How many electrons are racing through your phone at any given second? It turns out it's an enormous number. This number. I'm pretty sure you can't read that number. Try it. Give it a try. I don't know. Maybe you can. It turns out I did some practice here and I read it. It's 16 quintillion, 20 quadrillion. So that's a lot of electrons racing through your phone every single second. So clearly, when we have this picture of a battery here with just 4 electrons shown, that's just a representation. There's actually hordes and hordes of electrons flowing through any circuit that we have around us. Here's the thing. Our electrons are flowing from negative to positive, and that kind of makes sense. But it turns out, for reasons that are a little strange, current flows from positive to negative. So even though you see the electrons going one way, the current actually is flowing the opposite direction. Current flows in the opposite direction of electrons. Let's think about current in the context of a circuit diagram. On the left here, you see our battery, or our voltage source. The positive side is on top, and that's where the current is going to flow out from. So it's going to go up and proceed clockwise through the light bulb back to the negative terminal. This is just by convention. That means we made this up. And in fact, what actually travels through our wires is just the electrons. So there's nothing actually flowing from positive to negative, and this sounds pretty stupid. Why did we do it this way? The awkward truth is that current was defined before we knew about the electron. So this is what's called conventional current. Historically, we define current as going positive to negative, but nothing's actually moving in that direction. If we could go and redefine current all the way back in history, we would, but we're stuck with the history we live in, alas. So it's the electrons that are actually moving, and they move from negative to positive, But we do want to remember that conventional current is defined in the opposite direction. All right, when our electrons actually walk across this whole path, it's called direct current. It's when electrons flow from one part of a circuit to another. So you can imagine the wire being sort of like a racetrack and the electrons like runners that have to complete a whole loop. Let's look at a diagram of what this looks like at the atomic level. In a second, we'll see a picture that shows a bunch of nuclei, and they're going to look like this, and electrons. They're going to look like this. So here's a picture of direct current. Those electrons are all moving to the left, as shown by those green arrows. Meanwhile, the nuclei shown in orange are fixed and still. It's almost like a pinball machine where the nuclei are bouncers, those things that stay fixed still in the pinball machine, and the electrons are the pinballs racing by. This direct current actually moves from one spot in a pipe to another. So you can think of it as being kind of like water through pipes. That's what direct current is like. Alternating current is very different. Notice here I have green arrows and blue arrows. Here the electrons are going to shake back and forth. So they'll move a little while to the left and then a little while to the right. So in alternating current, electrons shake back and forth. Here we can think about it more like water in waves, where even though these waves have been crashing against this cliff forever and there's definitely motion of your water, water's not moving from the left-hand side of this picture all the way to the right. Instead, it's oscillating back and forth, and that's what alternating current does. Importantly, when you plug something into the wall of your house, you're getting alternating current. So wall sockets provide alternating current. What the cool kids call alternating current is AC, just the abbreviation. So wall sockets provide AC. Here's the thing though, lots of our electronics, like the phone you see here, like the computer you see here, require direct current. So electronics often require direct current. And what do the cool kids call direct current? You guessed it, DC. I'm not really sure who these cool kids are that use DC and AC, but you need to be one of them and know that direct current is DC. Now, how do we get the AC in our walls to become DC for our electronics? We use these bad boys. You've probably seen them hanging off of your laptop charger. And the blocks on these chargers switch AC to DC. These blocks show up in all different shapes and sizes on your cell phone chargers, etc. And they have a fancy name. They're called rectifiers, and they switch AC to DC. All right, now is your chance to practice what you've learned. Pause the video and see if you can answer each of these questions. Use your notes for a question bank. All right, let's review them. Current is measured in amperes. So amperes is the unit we use to measure current. Current that runs like water in a pipe is DC, that is direct current, where it actually moves from one place to another. Current that moves back and forth is AC, so that's where the electrons kind of shake back and forth. Electronics requiring rectifiers do they use AC or DC? Well, they use DC. AC comes from our walls, and we convert that to our DC with a rectifier. If current is running clockwise, then the electrons are moving counterclockwise. So remember that current and our electrons are defined in opposite directions. Let's review what we've learned. First, we introduced current as the flow of electrons through our circuits. Then we compared the flow of current and electrons, where we saw that because of the oddities of history, the direction of current and the direction electrons move are opposite. And lastly, we compared direct current, where our electrons move from one place to another, to alternating current, where our electrons shake back and forth.
Hey, hey.